If you want to surpass 99% of AI researchers, you need to do mechanistic interpretability. Now you're thinking, oh my god, this is like just trying to understand what current systems do as opposed to inventing new systems. I want to invent new systems. But Ilya Sutskever, the best AI researcher, one of the best, said that if you want to invent new systems, you need to understand the current ones. And understanding current ones is more important and better to invent new systems than trying to invent new systems. Just trying to come up with new ideas. This is why I'm learning mechanistic interpretability. If I, for example, want to work on optimizers, to create a better optimizer which will speed up entire field, because the entire field of AI is based on optimizer, which is basically the most fundamental way AI learns. Then I need to understand deeply the current optimizers, the math behind it, how it works, and the shortcomings in order to invent new optimizer. I cannot just try to invent new optimizer without understanding current ones. I want to try to either invent a new optimizer which is base of entire field, so that would improve entire AI field, or just try to do some research to help other people invent it. And for that, I need to understand the current optimizers as opposed to just blindly trying to get new ideas. So we will check this paper, Open Problems in Mechanistic Interpretability. This is way more important than you think. Understanding current ideas way more important than coming up with new ideas without understanding deeply current ones. Large language models produce text that closely resembles human writing, and it is tempting to assume that they generate it through cognitive processes similar to those of human writers. So the main argument is that humans and AIs use completely different representation space, which means, or representation processes, which means like the way of thinking. For example, some 4-year-old kids can master things that best LLMs cannot even do, but also humans cannot predict protein structure, protein folding that AI can do. Funny thing is, neural networks can think in completely different ways. For example, identifying fish by the fingers that proud fisherman uses to hold them. Even for some simple calculations, a transformer model was using Fourier transforms and more complex math to solve the tasks. All this is to say that neural networks and humans think in different ways. So to understand them, we need to be able to reverse engineer them. And the reverse engineering follows 3 steps. Is it in software engineering or neural networks, some mechanical hardware? It's always these 3 steps. Step 1, decomposition. Break down the object of study into simpler parts. Description of components. Formulating hypotheses about the functional role of component parts and how they interact. A process that can be called interpretation. Validation of descriptions. Testing if our hypotheses are correct. This also shows the same thing. We have neural network on the left and we have these components on the right. So we are decomposing neural network to figure out how components work, the role of each component. On the other hand, we have this concept-based interpretability as opposed to reverse engineering. So this is trying to discover human understandable concepts inside of neural network. If our hypotheses are invalidated, we must either improve our decomposition or improve our hypothesis regarding the functional roles of its components. We must systematically examine each step, analyzing current methods and their respective shortcomings. This is so true. Deep understanding. So in this research, mechanistic interpretability, we want to decompose neural network to study how its parts work in isolation. So then we need to understand how to decompose it at its joints. At which parts should we decompose it for the purposes of studying this? So they tried just isolating a single neuron or a single convolutional vector, and they found that actually a single neuron or single vector will activate for different things that neural network does. So it doesn't have just one function. Same goes for attention heads in the transformer. They also exhibit polysemanticity, meaning that they activate and have different functions. And studying the attention patterns of models can be often misleading. This is all to say that natural architectural components like attention heads, neurons, or layers do not provide a natural way to decompose neural network representations. So they don't actually have these, they are not like separate features that we can decompose and study. This guy is very popular, sparse autoencoder, and I will try to use this in my research on optimizers to try to figure out what current optimizers do well, what they don't do well, and maybe how to go towards even better next optimizer. Improved mechanistic understanding of model training could enhance the ability to predict when certain capabilities will appear. For instance, it has been observed that new model capabilities can emerge as a function of scale. Also, new capabilities can coincide with abrupt changes in the trajectory of model parameters. So for example, when all of a sudden, so when you have some amount of compute and you add more compute, keep training, and all of a sudden it speaks a foreign language that it didn't know how to speak. So mechanistic interpretability can help you predict these things, which is very good. So you don't blindly invest compute and training. So we have linear representation hypothesis, which is the idea that features and concepts are represented with a linear transformation of multiple weights and features, not just one single neuron, one single weight, for example. So the linear representation hypothesis states that the map from concepts to neural activations is linear. So a multiplication or addition. Superposition in this context means that neurons can represent different concepts in different situations when different parts of neural network activate. And then this sparse dictionary learning is used to decompose this superposition back to these simpler, more understandable representations. So this is how to study functional role of the blue component. For example, this one, component of interests in neural network, this can be attention heads, activations, keys, queries, whatever. So there are multiple ways to study it. We can look at the input components, which are purple input components and the red intermediate components. They feed into the blue component that we want to study, so we study this input, the prior components. We can also study its effects, like the orange output components or green intermediate components after the blue component. So they give a few examples of what you could do to study them. You can use these methods like activation steering. So these are additional reasons for studying mechanistic interpretability. Besides the main reason that I said, we need to understand current systems if we want to develop new, better system, not just trying to come up with new ideas without understanding current systems. So other benefits include, it's better explained here, so monitoring and auditing, spotting unsafe or biased behavior in AI, and then controlling, changing or steering model behavior, predict how it would behave in new situations. So this directly ties into making better models. So we can have better human interaction, more modalities, learn how to add more modalities, better inference training, which is exactly what I'm trying to do. I mean, we're all trying to do, especially better training. And then getting better regulations and laws. And then we have this summary of open questions, which is very interesting. They are so good. For example, to what extent do models encode concepts linearly in their representations? It's so interesting. How should we decompose neural network into parts? There are so many interesting ones. these are all good research questions. I'll quickly scroll through all of you to check it out. But there is quite a bit. So I think that's gonna be it for this video. What is interpretability? What are goals of the field? How should success be graded?